Hello everyone, and welcome to our class video where I introduce you to the idea of a formal mathematical proof. Our learning goal for this video is that you'll be able to understand the structure of a mathematical proof and apply it to prove solutions to algebraic equations. So let's get started. So what do I mean exactly by prove? Well, a proof is an argument that uses deductive reasoning to prove that a conclusion is true. It's like a formal way to show the progression of your thinking, similar to how you would show your work in an algebra problem, but here we are showing why a certain geometric property is true. However, we're going to begin by just looking at proof for algebra situations so that you guys get comfortable with the idea. So, consider how a proof is a contrast to a counterexample. By the way, this is more of a side note. You don't have to write this part down. A counterexample, if you recall, is an example that proves a statement false. To prove a statement false, you only have to provide one example that shows that it's false. After that, we know the statement is wrong. If you want to prove a statement true, however, you must use deductive reasoning, starting with some facts that everyone agrees on, and then conclude that your proposition is true for all cases. But it only takes one person to prove you wrong with one counterexample for your entire argument to fall apart. And by the way, it might also be good for you to know that sometimes a proof is called a derivation for significant mathematical properties, like if we are deriving the Pythagorean theorem. There are three main types of proofs. The one we will focus on most in this class is the two-column proof, which obviously, by the name, is in two columns. However, you should also know that there are paragraph proofs and flowchart proofs. We might barely touch on those this year, but our emphasis is going to be on the two-column proof. Okay, now, in your notebook, you have been provided this resource. Depending on when you're watching this video, you will have either already received this or you will soon receive it to put into your notebook. This is a list of properties that you can use in algebraic proofs. Some will be used more than others, but I'll highlight the most significant ones. We'll take a look at all of these more in detail in class. You might want to star these in your notebook. The substitution property is one that seems to come up a lot. If we're solving linear equations, that is, with a power on x that's no greater than 1, these properties you hopefully will recognize are ones that we're using most of the time. Additionally, when we're solving quadratic equations, those last two are of particular importance. Okay, so we'll look at that later, but let's just look at a couple examples. Okay, so here's our first example. Given that 3 times quantity 2x plus 2 equals 30, prove that x equals 4. Okay, pretty much all proof problems have a given and a proved statement. You're proving that if that part is true, it is given to you as already true. Then we are going to prove that x equals 4. Okay, so as I said, most problems the final conclusion for you is already given, and you just must figure out how to reach it. However, this isn't required in all types of proof situations, such as when mathematicians are proving new things that haven't been proven before. Okay, so when we make a two-column proof, divide a section of your paper into two, and then we're going to have one column entitled Statements, and another one for the reasons those statements are valid. In each column, we'll number the statements so that it's obvious which one goes with which. The first statement is always our given information, so we'll write down our initial equation. And the reason for that first statement is always that it was given to us. This is our starting point. We are assuming that that is true. Okay, so then let's walk through this step by step and give the reasons why each step is true. What would be the first thing we would do to solve this equation? Well, hopefully you're thinking that we would use this. In this case, we would use the distributive property. If we distribute, then our equation changes into 6x plus 6 equals 30. And the reason that we are allowed to change the equation like that is because of the distributive property. Okay, so what would we do next to solve for x? Well, we would need to subtract 6 from both sides. We know that we can do this because of the subtraction property of equality, which is listed on that previous page, which says for all numbers a, b, and c, if a equals b, then we are allowed to subtract c from both sides, and the equation still remains true. Okay, so after we subtract 6 from both sides, we would have 6x equals 24. Okay, and our reason for that is the subtraction property of equality. Notice how I'm abbreviating. Okay, and what is our next step? Well, it would be to divide both sides of the equation by the coefficient of x, that is 6. We are allowed to do this because of the division property of equality, which, similarly to the subtraction property, states that we can divide both sides of an equation by some number given in the property as c. I can divide both sides of the equation by that number, as long as c isn't 0, and the equation still remains true. After I use the division property of equality, this final step of the equation is x equals 4. I have thus proved what we set out to prove. That's good. So we have just proved that if 3 times quantity 2x plus 2 equals 30, then the value for x is 4. Okay, so let's look at one more example. Let's look at a quadratic example. Those are fun always, aren't they? Okay, so once again, to set up the 2-column proof, divide a portion of your paper into 2 columns with one column for statements and the other column for reasons. Do you remember what the first step is going to be? Well, the first statement is always our given information. So I'll write it down. X squared equals 7x plus 18. That's given. What are we trying to prove here? We're trying to prove if that equation is true, then we know that either x equals 9 or x equals negative 2. Okay, so what would I do here? Well, recall that our strategy on quadratic equations is to move all terms to one side of the equation, leaving 0 on the other. What would I use to do that? Well, in order to do that, I would need to bring the 7x and the 18 over to the left side. If I did that, I would have x squared minus 7x minus 18 with 0 on that side. What's my reason? Well, I subtracted things from both sides, so my reason is the subtraction property of equality, which says that if a equals b, then I could subtract something from both sides and still have the same equation, or still have a true equation. So, once again, we are using the subtraction property of equality. And again, it's okay to abbreviate. Alright, then what's our strategy after that? We need to find two numbers that will multiply to give negative 18 and add to give negative 7. And we usually write it like this. Don't forget the equals 0 over here. Okay? What are those two numbers? Well, if you think about it a little bit, those two numbers would be negative 9 and positive 2. They multiply to give negative 18, and they add to give negative 7. Now, what's my reason for this statement? The reason for this is we can do that is because of the converse of the distributive property. Huh? Well, let's take a look at it. So, it says for all numbers a, b, and c, okay, if I got that, ab plus ac, I can factor out the a. I'm undistributing here. Is that what I just did? Well, yeah. If I were to redistribute in these cases, then I would get my original equation back. Okay, let me clear up some of that mess. So what's our conclusion after that? Well, most of you would say that we can conclude that either x equals 9 or x equals negative 2. But hold on, we're actually skipping a step there. Really what you mean is that x minus 9 equals 0 or x plus 2 equals 0. Why is that? This is because of the zero product property, which says that for any two numbers, if a times b equals 0, so again, if two things multiply to give 0, then either a has to be 0 or b has to be 0. So we know that either x minus 9 has to be 0 or x plus 2 has to be 0. Then we can set about figuring out what makes those things 0. Okay, so I'm using the zero product property here. Now then, we can come to our conclusion. Now we know if x minus 9 is 0, the value for x that makes that 0 is 9. And if x plus 2 equals 0, then the value for x that makes that 0 is negative 2. This is effectively the same as adding 9 on both sides or subtracting 2 on both sides. So what's our reason for this statement? Well, given that one is addition, one is subtraction, this is the addition or subtraction property of equality, similar to what we did in step 2. Okay, well, hope that all makes sense. It takes a little bit of getting used to, but I bet you'll get used to it. So just give it some time. Alright, well, I will see you all in class.